Bismillahirrahmanirrahim. Today we are going to speak about the Green Theorem in the plane. Green Theorem is one of the theorems that relate the double integral and the line integral. Sometimes we call it the transformation between the double integral and line integral. The statement of the theorem says that let R be simply connected region. Simply connected means it is non-self-intersecting. It has or there is no hole between or inside this region R. So let R be simply connected region whose boundary is a simple closed piecewise smooth curve. Simple, it is continuous and non-self-intersecting closed piecewise smooth curve C, oriented counterclockwise. So oriented counterclockwise just to keep the region R to the left of the movement. If P of x, y, Q of x, y, and partial derivative with respect to y, partial derivative of Q with respect to x are continuous on R. Then the line integral given by integration of P of x plus Q dy along the curve C is equal to partial derivative of Q with respect to x minus partial derivative of P with respect to y dy or dA. So we started with line integral. If these conditions are satisfied, that R is simply connected and the boundary is simple, closed, and piecewise smooth curve, then the line integral equal to the double integral of the difference of the partial derivatives Q sub x minus P sub y dA over the given area or given region R. So the idea is just to relate the line integral and the double integral. As direct application for this one, let's have some examples. Let's evaluate this one. Evaluate x squared minus y squared dx plus 2y minus x dy. Where C consists of the boundary of the region in the first quadrant that is bounded by the graphs of y equal to x squared and y equal to x to the power 3. So R is just the region enclosed between these two curves, y equal to x squared and y equal to x to the power 3. And we need to evaluate the line integral. So let's see the curve of R. I have y equal to x squared, so it is parabola. And we have y equal to x to the power 3. That will be something like this one. You know, the graph of the y equal to x to the power 3. So R will be the area enclosed between these two curves in the first quadrant. So we ask me about the first quadrant. Now, this is R. For the line integral, I have B equal to x squared minus y squared. So B sub y equal minus 2y. Q is equal to 2y minus x. This will give me q sub x equal to minus 1. And to take the direction of the counterclockwise, use this as direction of the curve, moving counterclockwise. So we have curve oriented counterclockwise. We have continuous function b of x, y, q of x, y. All of them are continuous, R is a closed symbol, and oriented counterclockwise. So all the conditions for the Green theorem are satisfied. So the line integral can be converted to double integral. The line integral can be converted to double integral to evaluate. So the line integral now, which is given by c of x squared minus y squared dx plus 2y minus x dy is equal to double integral over r of the derivative, this is b, q of x, which is minus 1, minus b sub y, which is minus 2y, dA. Now for the double integral, we have type 1 or type 2. Type 1, we are using in type 1, we are using the vertical bar. That is y equal to f of x, and down is y equal to g of x. So if you use type 1, using type 1, using type 1 means using the constant limit for x and writing y as a function of x. We are speaking about type 2, we will use the constant limit for y and writing x as a function of y. So type 1, I will have now minus 1 plus 2y, start with dy dx, keeping the x for the constant limits. Now, for the limits of y, the lower function is x to the power 3, and the upper one is x to the power 2. To find the limit of x, we know this point is 0, 0, down. The upper point is intersection point, so I have to make y1 equal to y2 and solve it. So y1 equal to y2, which is equal x to power 3 equal to x to power 2, or x to power 3 minus x to power 2 equal to 0. Take x squared as a common factor, I will have x minus 1 equal to 0. So x will be 0 or x equal to 1. So the limits for x are 0 and 1. Now integrate. Now to integrate with respect to y, I will have the outer limit, or integration, keep it as it is outside. I will have minus y plus y square from x to power 3 to x to power 2 dx, which is equal to integration of 0 to 1. It will be minus x square plus x to power 3, this is for the first one, plus x to power 2 all to power 2 minus x to power 3 all to power 2 dx. this can be written as 0 to 1 of minus x to power 3, just reorder the terms, plus x to power 4 plus x to power 3 minus x to power 2 dx. So we'll have x to power 6 minus 1 over 7 x to power 7 plus 1 over 5 x to power 5 plus 1 over 4 x to power 4 minus 1 to power 3 1 over 3 x to power 3, the limit between 0 and 1. So this will give me minus 1 over 7 plus 1 over 5 plus 1 over 4 minus 1 over 3. Find the common denominator for this one. 3 times 4, 12 times 5, 16 times 7 equal to 420. So this is, using the calculator, you will have minus 11 over 420. So the value for this integration is equal to minus 11 over 420. So all what we did, we use the Green Theorem to convert the line integral into or to double integral, and we evaluated to find the area. Let's take another example. Let's evaluate or use the Green Theorem to evaluate the integration C of x squared dx or x squared y dx, say, plus x dy along the triangular path. The vertices zero, zero, 1, 0, and 1 and 2. So the curve C is given by triangle. It is 0, 0, 1, 0, and 1 and 2. And if we go counterclockwise, so we can see that C is closed, simple closed, oriented counterclockwise, and R is given there as a simple region. So this one can be done now by converting the line integral into double integral. So by the Green Theorem. this is equal to, this one is b and this one is a q. So it is q of x minus b sub y dA over r, which is equal to q sub x is equal to 1 minus b sub y is x squared. We differentiate q with respect to x, I will have 1, and differentiate p with respect to y, I will have x squared over r. Now this is r. I can use type 1 or type 2. For type 1, up to down. This is y1 and y2. So it is 1 minus x squared dy dx. We need to find the limits of the variable y. The lower limit, it is equation of x-axis. And for the x-axis, it is y equal to 0. So the lower limit is 0. Now the upper limit is the equation of a line. I have 1, 2, and we have 0 and 0. y1 is equal to, the slope for this one, since it's passing through the origin, it is y over x. 2 over 1 multiplied by x. And there is no y-intercept, or the y-intercept equal to 0. So y2 equal to 2x. So it is from 0 to 2x. And the limit for x start from 0 up to this point, up to 1. So the limit for x are from 0 to 1. So we found the limit for y and we found the limit for x. Now we can integrate. So the integration for this one now with respect to y first will give me 0 to 1 of y minus x squared y. Or just because there's no y, I can write it as y minus 1 minus x squared multiplied by y dx, and y between 0 and 2x. That will give me integration from 0 to 1, replace y by 2x, and then by 0, I will have 1 minus x squared multiplied by 2x dx, or it is 0 to 1 of 2x minus 2x to the power 3 dx. Integrated, or integrate this with respect to x, I will have x squared minus 2 over 4x to the power 4 from 0 to 1. And the value for this one will give me 1 minus 2 over 4 multiplied by 1. That will be 1/2. So the value for the line, for the given line integral equal to 1/2. And we use the Green Theorem to convert it from line integral to double integral. So this is the direct application for the Green Theorem, transforming the line integral into double integral to make it easier to evaluate.